So what did we learn before the break? We started a new topic, magnetic field, right? So I believe everyone has played with magnets when we are little, right? When we're kids. So every little magnet you see, there's always a north and south pole, right? Always. And then these poles, they interact with each other, right? They also have these little compasses. They're also going to respond to these magnets, right? And the interactions between these poles are very similar to the interactions between the electric charges, right? So that's already a hint that they may be connected, right? So like poles repel, unlike poles attract, right? So but there's a difference, as we said before the break. You cut this guy into half, you don't get a north or a south, right? You still get a complete north and south, and then another complete magnet with north and south. Okay, so that's very weird. That's we don't know why, but that's what we discover in nature. There's no isolated north or south poles. We call them magnetic monopoles. So we don't have any evidence for magnetic monopoles. Okay, so that's a big difference from electric charge. So that's why when we want to construct a theory for magnetic field, it's very hard, right? Because we can do this, right? First of all, we can say that there is a magnetic field. Okay, for a magnet, I can draw the field lines to help me visualize the magnetic field. And then our convention is that when you draw the magnetic field lines, they always they start on the north pole. They're going to go back to the south pole, outside the magnet. So that's how you would draw the magnetic field lines around the magnet, right? The magnetic field created by this magnet. But they don't stop on these ends, okay? They will continue to form a closed loop, okay? So they will continue inside the magnet. But usually we're not interested in magnetic field inside the magnet, right? If I want to make use of this magnetic field, I would just use the magnetic field created by this magnet outside it, right? But inside it, remember, they still form closed loops, right? So they will go from south to north, actually, inside the magnet. Right. So again, that's because there's no isolated north pole or south pole, right? So and that's why it's difficult to construct a theory for magnetic field like what we did with electric field, right? How do we construct a theory for electric field? Well, we first define the electric field as this, right? If there is an electric field, I want to find the strength. I want to find the field vector at any point. I would bring a test charge in that electric field, right? And then measure the force on the test charge, and then I divide the force by the test charge. That's going to be the field strength, the field vector at that point, right? So you can do that in principle. You can do that for every point in the electric field. Then you will have all the field vectors at every single point. So you know everything about this electric field. Okay, and then using that definition, we started with a positive charge, right, or negative charge, either way, right? Then we figured that you can use this definition. You start with Coulomb's law, and then you can derive an equation for the electric field created by a point charge, which is going to be this. Right? So this guy is charge Q. And then the direction, well, our convention is this, right? Our convention is for positive charges, the electric field lines, they are going away from the positive charge, and then they go toward the negative charge, okay? But you can't do this with the magnetic field because we don't have this guy, or this guy, right? We don't have an isolated north or south pole, so that you can first use a test pole in the magnetic field and then measure the force divided by the test pole, and then draw these lines, right, starting from a north pole or south pole, because you don't have these guys. So this is you can do it this way, okay? But fortunately, As I usually say, nature has been very kind to us. God has been very kind to us. So physics discovered that an electric charge, a charged particle, moving in a magnetic field, right? So like this guy, if it's positive charge, moving in the magnetic field created by a magnet, it's going to behave as if there's a force pulling it in some direction. And that force can only come from the magnetic field, right? Because it's in the magnetic field. It's not in the electric field, right? So, and this, again, this is very weird, right? It's not very intuitive. But why it's not very intuitive? Because we don't have experience with that. When you say something is intuitive, that means you have experience with that, right? If you don't have experience with this guys, right? Have you ever seen this, like a moving charge in magnetic field? No. Have you ever done an experiment like this? No, right? So that's why it looks, it seems very non-intuitive to you. But physicists have done this experiment many times. Okay, there's always a force from the magnetic field on this moving electric charge. Okay, so then they wanted to study that force, right? So they did a lot of experiments. So and then I summarized all the facts they found in slide 7, lecture 11. Okay, now we're on lecture 11. So I'm just going to tell you which slide I'm on. So you will. So when you watch the video, you're going to have the lecture on the side, and then you know which lecture and which slide I'm on. Okay. So all these facts on slide 7. Okay. These are the facts they found. Okay. And then they found that this is really, really smart. You can summarize all these facts in one equation. Very nice equation, okay? So that's the equation they found. So if there is a electric charge moving in a magnetic field, okay? So the magnetic field will have a force on this moving electric charge. And the force can be calculated this way, using a cross product defined by mathematicians. Okay, so usually these mathematicians, they define a lot of tools. They don't even know what the use of these tools. Okay, and then physicists, when they study some new physics, they realize they have to use these new mathematic tools. So it's very amazing, totally amazing. Okay, so how do you use the equation, this equation, to figure out the force on the electric charge? This Q is the charge, right? So it can be positive or negative, but it's a scalar. It's a number with a sign. The V is the velocity vector of this charge, right? When this charge is moving this way, this is the velocity of this charge, right? And the B is the magnetic field. We use this symbol to denote the magnetic field with an arrow on top of it because it's still a vector, right? Any field is a vector. It has both magnitude and direction. So the magnitude, and then when you find a force, a vector, so you always do that in 2 steps, right? You find its magnitude and its direction, then you know all the information for this, about this vector. So the magnitude of this guy, easy, you just use the definition of a cross product, right? The cross product between 2 objects is still a vector, but the magnitude is the product of these 2 vectors and then the sine theta. So this guy, so Q, okay, you make it positive, right? Because you're calculating the magnitude of the force. Everything's going to be positive. And then V and B, they're just magnitude of the velocity and the magnetic field, okay? And then sine theta. The theta angle is going to be the angle between these 2 vectors, right? Because there are only 2 vectors in this equation. The sine theta, the theta angle must be the angle between these 2 vectors, okay? So that's how we can calculate the magnitude of force. And you see that then we can define magnetic field, right? So you can first measure the force when there's a moving charge in the magnetic field. And then you can measure the charge, you can measure the velocity, you can measure the angle between these 2 vectors, and you divide both sides by all these variables, you get this B, right? So that's how we define magnetic field. And the unit for magnetic field, we call it Tesla, okay? So that's the SI unit for magnetic field. And Tesla is actually a very large unit, okay? So that's very important when you solve a problem, okay? Usually a magnetic field of 1 Tesla, it's already very strong. That's the magnetic field. That's the order of the magnetic field in the MRI scanner. Okay, it's already a very strong magnetic field. That's why these MRI scanners, they're very expensive, because it's actually very hard to create a magnetic field in that order. Okay, so if you solve a problem, right, you get a magnetic field like 100 or 1,000 Teslas, you have done something wrong. Because in reality, that's really, really hard, okay, to create a magnetic field that large, okay. Usually, it's going to be smaller than 1 Tesla, okay. So that's the magnitude, right? So you just plug all the numbers in, you can find anything you like. You rearrange this equation. Direction is a little bit weird, right? You're going to use, so basically, you're going to first find the direction of this cross product, which is going to be perpendicular to both of them. So the direction of the force is going to be perpendicular to both the velocity and the magnetic field. Again, it's very non-intuitive, right? So this guy is moving this way, and the magnetic field, say, is in that way. The force is going to be in neither of these 2 directions. It's a third direction, which is perpendicular to the B and V, okay? So again, as I said, why it's not so weird? Why is it so non-intuitive? Because we don't have experience with these guys in our life, right? And then how do I believe this theory? Well, we can do experiment. The easiest way is to do an experiment to test the theory, and we will do experiment, but not for now, because I can't grab a single electron or proton or a single charged particle and then let it run in the magnetic field and show you the force, right? But there is a smart way to test the theory. There's a smart way to find out the force on the moving charge, magnetic force, and we're gonna see that in a little bit later, okay? But now let's first practice this law, right? As I said, the direction of the force is going to be perpendicular to V and B. Okay, so you're going to draw these 2 directions, V and B, and then you find the direction of this force. And also, this direction of this force depends on the charge, the sign of the charge. So the direction of the force is going to be different if you replace the charge, positive charge, with the negative charge. Okay, so this is very hard. Okay, we're dealing with 3 directions, so that's why we have this shortcut called right-hand rule. We don't have many shortcuts in physics, but this is a shortcut to help us find the direction of the magnetic force on a moving charge. Right. So the right-hand rule is this: you first put your 4 fingers in the direction of V, whatever the first vector is. Right, that's the cross product. You curl your 4 fingers, okay, into the direction of the second vector, which is the magnetic field, in this case, okay? And then you're gonna try it, okay? At the end, you're gonna find one unique way to do that, okay? And then your thumb is gonna be pointing in some direction, right? So now you're gonna take a look at the direction of the sign of the charge. If the charge is positive, moving in that direction, magnetic field, now your thumb is the direction of the force it feels. Right. If it's a negative charge, then you're going to flip the direction. Your thumb is in this direction. The force on this negative charge is going to be the opposite direction. Okay, so this does require a lot of practice because this is not intuitive at all. Right. So that's what we started doing last time. Right. And then in this case, when we deal with 3 directions, when we want to draw 3 directions on a piece of paper, it's hard. So that's why we use these symbols. We use dots and crosses to represent a direction perpendicular to the page. Right? So our convention is this: if we draw dots, we mean that there's a direction of a vector coming out of the page. Out of the page. So this is out. And then when we draw a cross, we mean that there is a vector going into the page. In that way, okay? So this is out of the page. So in this case, we can draw 3 directions on a piece of paper, right? So you still use this plane to draw 2 directions, and you use dots and crosses to represent another direction perpendicular to the page. Okay? So we did some practice before the break. So that's lecture 11, slide 11, slide 12. Okay? So now we're gonna do more practice so that we get familiar with this rule, right? As I said, this is not intuitive, right? When it's not intuitive, you have to do a lot of practice on it, right? So now let's take a look at the next question, slide 13, okay? So on this slide, we still, okay, so we did the, if you review the questions on slide 11 and 12, we did the, use the right-hand rule to find out the direction of the magnetic force on these moving charge, right? For example, let's redo it. Slide 11, we have a magnetic field down, right? And there is a charge moving to the left, no, moving to the right, sorry. Okay, so this charge has a velocity to the right. Okay, what is the direction of the magnetic force on it? Put your 4 fingers in the direction of V, right? Okay, so that's V. I want to curl them into B so that I have to rotate my hand a little bit, right? So my palm is facing down so that I can curl my 4 fingers down into the direction of B, because B is down. And there's only one way to do that, right? And then you see that now my thumb is pointing into the page. Okay, but wait a minute, take a look at the sign of the charge. Positive charge moving, okay, so the force is, the direction of force is the thumb. So this guy is gonna feel a force into the page, okay? Very weird, you see that the field is down. This guy is moving to the right, but it feels a force into the page. So it's gonna be moving this way actually. It tries to move straight in that direction, but it feels a force pulling it in that direction. So if it deflected that way, it's not going to be deflected in the direction of the B, okay? Which is very weird. But again, as I said, this is what we discover in nature, right? You can't argue with God. I don't like this universe you created. I created another universe for me. No, okay? And then I also said we will have an experiment to test this theory, okay? You will see this is true, okay? All right, and then question, the slide 12, we did something similar for negative charge, right? For negative charge, so, okay, let's redo it. So what you're gonna do is that if the magnetic field is out of the page, right? You see a lot of dots. So there's a magnetic field coming out toward you. Okay, you see the magnetic field coming out toward you. Now there's a negative charge moving up in this region. So this is a negative charge. It wants to move straight up. But again, the magnetic field is going to have a force on it. So it's not going to let it move in that direction. What is the direction of the force? Right-hand rule. Put your 4 fingers in the direction of V. Velocity, okay, this way. Now you want to curl them out of the page, right? So sometimes you need to rotate your whole body, okay? So in this case, it's easier if I'm facing this way. V's up, I'm gonna curl them out of the page. So what is the direction? Direction, it's gonna be in this direction, right? Out of the page. And then what is the direction of the force on this moving charge? Well, that's, oh no, that's right. So that's toward the right. So if you do that, you're gonna see this is the, okay, I'm confusing myself. I'm still looking at this problem. So up, and then I want to curl my 4 fingers in the direction of B, so that's how I curl them, right? So then my thumb is to the right, So, but wait a minute, what is the sign of this charge? The sign of this charge is negative. So that means the force is not going to be in that direction. The force on this guy is going to be to the left. Okay? So this guy tries to move up, but it's going to feel a force in that direction. So this guy, the magnetic field is not going to let it do it. It's going to pull it in that direction. So again, it's very weird, right? The magnetic field is actually in this direction, but it's going to pull the charge in that direction. Okay, very weird, but this is what happens in nature. So in this case, the direction is to the left, right? You do this, okay? Now let's do this. So a lot of people, they will make this mistake. Once they have learned right-hand rule, they have learned magnetic force, they forget about the electric force. Okay, how do we determine the direction of the electric force on a moving charge? Okay, so take a look at slide 13. So in this case, still this image. Now I'm going to do this, right? So the electric field, so there's an electric field down in this region. This charge moves in that way. What is the direction of the electric force on it? Electric force, not magnetic force, right? Again, a lot of people, I believe you're also trying to do this, right? I'm going to do V toward, wait, this is not B. This is not magnetic field. You don't use this theory, right? You're going to use the theory for electric force. Why do we do this? Because we will have a combination of electric field and magnetic field in this part. Okay, we were going to see both. Okay, so that's why we still want to review the electric force on the electric charge. What is the theory to find out the electric force on a charge when there is an electric field in that region? That's the theory. Right? That's the theory we learned in electric field. If there's a charge in the electric field, the force only has two options, right? Still remember that? Either the same with the field or opposite to the field, right? So you don't need to do any right-hand rule, okay? So that's why we want to do this. A lot of people, once they learn right-hand rule, they just do that for every force, okay? Electric force, no right-hand rule. Thus, right? So electric field, this is the electric field down in this region. This is a positive charge. This guy is going to feel a force the same in the direction of the electric field, right? Because it only has two options, either the same or opposite. Has nothing to do with the V, right? Doesn't matter if this guy is moving or not, right? So in this case, what is the direction of the electric force on this guy? Down. Right? So electric field is down, the force is down. So that's more intuitive to us, right? The field is in that way, so the force is also in that way. But this is electric field, right? This is actually easier than magnetic field, magnetic force, okay? So if you want to find out there's a magnetic field, there's a moving charge in the magnetic field, you do this to find the magnetic force. If there's an electric field, right? And there's an electric charge moving in that electric field. You do this, and this is the easiest theory, right? Either opposite or the same with E, right? Depending on the sign, okay? So don't forget this, don't forget this. We will have a combination of electric field and magnetic field in this part. So that's why we want to do this. I want to remind people, okay? So that's slide 13. Okay, when we do these questions on these lectures, okay, I want you to also, so I can't have you do iClicker now, but I want you to also do everything, okay, before I review the answer, okay? What you can do is that after I explain things, you may just pause the video, right? Because now you can always pause anytime. So I think this actually, it can help some people even learn better, because you can always pause the video. You can watch the video many times as you like, right? So this could be a good thing for some people, okay? So yeah, pause the video, do solve this problem, okay? And then see if your answer is the same with my answer, okay? Now let's take a look at the slide 14. Again, it's the same image. So what I do is this. Now, no magnetic field, it's an electric field. This is the electric field. Electric field coming out of the page, okay? Negative charge moving up in this electric field. What is the direction of the electric force on it? Again, okay? Okay, is anyone doing this? Okay, no, don't do this, because this is electric field. You want to find an electric force, no right-hand rule. Don't do anything here. Use this theory, easier. Two options, the force is going to be either the same or opposite to the direction of the field, if it's an electric field, right? Totally depends on the sign of the charge. Negative charge, so the force is going to be opposite to the field. That's it. No right-hand rule, no curling your fingers, no, okay? This is the direction of the field, out of the page. This is negative charge, so this guy is going to feel a force into the page. So the electric field on this guy is going to be into the page. So in that direction, okay? So this guy, when this guy moves up, it's going to be pulling actually in that direction, okay? The field is in this direction, but the force is opposite, so it's going to be pulling in that direction. So that's the electric field, right? Don't forget the electric field, electric force. They are easier actually than the theory for magnetic force, right? If you want to find magnetic force, right-hand rule, okay? If you want to find electric force, no, don't do right-hand rule. Use this theory, right? Either the same or opposite, okay? Now let's move on to, okay, now I want to also still have you do some practice to see the difference between magnetic force and electric force. Now let's take a look at slide 15, slide 15. Now slide 15, the same image. Now in this case, what do we have? Magnetic field, okay, so this is, let's replace this with magnetic field. Now this guy, what is the direction of the magnetic force on the charge if the charge is not moving? So let's assume this guy doesn't have any velocity. This guy just sitting here, okay? Okay, this guy's sitting here, magnetic field down, no velocity. What is the direction of the force on it? Think about it, try it. Using this theory, okay, pause the video, think about it, and then see if my answer is the same with your answer, okay? All right, so, okay, I'm just gonna assume you have done some work. Now I'm gonna tell you the answer. Magnetic field, you will do right-hand rule, right? But remember, the force is proportional to QVB and sine theta. The charge has to be moving. If the charge is not moving, it doesn't feel any magnetic force. It feels there's no field around it, okay? So in this case, no force, because it's not moving. So it's just gonna sit there forever, okay? Nothing's gonna happen to it, okay? The magnetic field is down, fine, okay? But the charge is not moving, so it doesn't feel any force because the force is proportional to the velocity. So it has to be moving in that magnetic field. Otherwise, it doesn't feel any force from the field on it. Very weird, right? Very weird. But again, this is what we found in nature, okay? You can't argue with that. Okay. Now, okay, the same image. Now this guy, now replace these electric fields with magnetic field. Now this is slide 16, okay, 16. Now, okay, now let's assume still a negative charge, but this negative charge is not moving here, okay? Again, sitting here, the magnetic field is out of the page, okay? What is the direction of the magnetic force on it? Okay, think about it. Magnetic force, you would use this theory instead of that one, right? Again, because magnetic force is proportional to the velocity of this charge. This guy, if you tell me it's not moving, it's just sitting here, okay, still, no force. I don't even need to do right-hand rule because the V is 0, right? As long as like, if there's one number here 0, then it's 0, okay? So in this case, still doesn't feel any force, right? It feels like as if there's no field around it, right? Very weird, but this is how magnetic force works on electric charge, okay? All right, now again, okay, the same two images. Now let's move on to slide 17. 17, replace this with electric field. Now electric field, what is the direction of the electric force on it if this guy's not moving? Okay, still no velocity, not moving. But what if this is the electric field? What is the direction of the electric force on it? Again, think about it, pause the video, think about it, okay? Electric force, no right-hand rule, right? Has nothing to do with the velocity. This is the theory, right? So even if this guy is sitting here, still not moving, the electric force is still on it, right? What is the direction? Either the same or opposite to the field, depending on its sign. Positive charge, okay? It's not moving, fine. It's still going to feel a force in that direction. So this electric field is not going to let it rest at that point, right? The electric field is going to pull it in this direction. And it's going to actually get faster and faster. So it can't stay still there, okay? So that's what electric force does. Again, this is actually easier than that, right? Electric force, electric field in that way. Electric force is also in that way because this is positive charge. So it's going to pull it in that direction. Okay, doesn't matter if it has velocity or not, right? The electric force is always going to be in the direction. You tell me this guy not moving, this guy moving in this direction, or this direction, or that direction, or this direction. Does that change the direction of the electric force? No, it doesn't, right? Because the electric force only is going to depend on the direction of the electric field. Of course, the sign of the charge, right? But it has nothing to do with the velocity, okay? Very different. These two forces are very different. But magnetic force, you will take a look at the direction of the velocity. You do right-hand rule, right? So if you tell me it's moving this way, that way, that way, that will change the direction of the magnetic force, okay? So electric field, no. Don't even tell me what this charge is doing. Tell me the sign of this charge. Positive, okay. Field it this way, electric field, force this way. That's it, okay? So that's slide 17. 18, okay? Again, the same image. Now replace this guy with electric field. Okay, electric field coming out in this direction. Okay, what is the direction of the force on this guy? If this electric charge is not moving in this region, okay, as I said, electric force, forget about that. This is the theory for magnetic force, right? Use this theory. I don't care if it's moving or not, right? Don't even tell me that information. Just tell me the sign of this charge. Okay, negative charge, the force on this guy, electric force on this guy, it's gonna be opposite to the direction of the field. Okay, that's it. What is the direction of the electric field? Coming out of the page. What is the direction of the electric force? Into the page. That's it. I don't care if this guy's moving, or this guy's moving in this direction, or that direction. The electric force still into the page always, because the electric force doesn't depend on the velocity of the charge, right? Magnetic force will depend on the direction of the velocity. You have to tell me if it's moving or what is the direction of its velocity, so I can do right-hand rule to find the direction of this magnetic force for you, okay? So I hope this practice help us to, first of all, get familiar with this law, this theory, and also see the difference between the electric force and magnetic force on a moving charge, okay? All right, so let's do more practice. Slide 19, okay? So what is this page? This question, find the direction of the magnetic field acting on the positive charge. Okay, so there's a positive charge particle moving, shown below if the direction of magnetic force acting on it is as indicated. Okay, so I'm going to erase this. We're done with these two images. right? So that means, okay, there's a charge moving, okay, I see. A positive charge moving in this direction. It feels a magnetic force up. So there is a magnetic force up. Because in this region, there is a magnetic field. Okay? That's why it feels a magnetic force, right? A moving charge in the magnetic field will feel a magnetic force on it. Okay, so now we're doing things backwards. I'm telling you, it feels a force up. I want you to find the direction of the magnetic field in this region for me. Okay? Well, okay. We learned how to use the right-hand rule to find the direction of force. But now you told me the direction of the force. I want to find the direction of the magnetic field. So we're doing things backwards, okay? So it's a little bit weird. So that's why we need to practice to get used to it. So what I'm going to do is this. I'm going to put my 4 fingers in the direction of V, right? And then if I want to find the direction of the force, I would curl it into the direction of B. But I don't know the direction of B. But I know at the end, I will have my thumb pointing up because that's the direction of the force you told me, right? So how do I do that? Again, you need to practice. You can try that, right? So try it yourself before I tell you the answer. Pause the video. Now, again, as I said, you're going to try it, okay? And then you're going to find there's a unique way you can do that. So in this case, I'm going to put my 4 fingers in the direction of V. How do I curl them so that my thumb is up? Well, I'm going to curl them into the page, right? So you see that V, what is the direction of B so that my thumb is going to be up? Well, if I curl my 4 fingers into the page, then my thumb will be up, which is going to be the direction of the force. The problem tells us, right? So that means the magnetic field in this region, it's going to be into the page. And this is a positive charge, right? So it has to be into the page. So when I do V toward B, my thumb will be up. Okay, so we're doing things backwards. We know the direction of the force. We want to figure out in which direction our 4 fingers are going to curl so that my thumb is up. Okay, so this does need some practice. Okay, so that's why we are doing more practice. So take a look at the question on slide 20. What is the direction of the magnet? So so let's draw it out. I'm going to erase this. Okay. This guy is coming out of the page. Okay, so a charge, still positive charge. Okay, that makes things easier. So imagine there's a positive charge coming out of the page. Okay, so the charge is moving towards you. In this region, there is some magnetic field. We don't know the direction, but we know that this guy is going to feel a force up at the end. What is the direction of the magnetic field? Again, you're going to do things backwards, so it needs some thinking. You're going to put your 4 fingers in the direction of V, and then try to curl your 4 fingers in some direction so your thumb is going to be up. Right, so you're going to try that, okay? So try that, and then I'm going to tell you the answer. So again, there's only one unique way to do that, right? So the V is out of the page, so I'm going to put my 4 fingers in that way, and then if I curl them to my right, 4 fingers and curl them to the right, so my thumb is up, right? You're facing this problem, okay? You're looking at this problem, okay? I have to put my 4 fingers this way. So if I curl my 4 fingers to the right, my thumb is up. So that means in this region, there must be a magnetic field in this way. Right, so I do a V toward B, my thumb is up, okay? So the direction of B must be to the right, okay? Now let's do a final practice. Okay, again, a charge moving into the page. Okay, so now imagine a positive charge moving in that direction, okay, into the page. Now it feels the force to the left at the end. So there's a magnetic field in this region, okay? So this is the last slide, 21. There's a magnetic field in this region. We don't know the direction, but all we know is that this guy moves into the page, but it feels the force to the left. How do I find the direction of the magnetic field? Put your four fingers in the direction of V, which is into the page, and try curling them to some direction so your thumb is to the left, right? Okay, so try that before I tell you the answer. Put your four fingers into the page, right? If I want to have my thumb to the left, I would just curl them down, right? So if I curl my four fingers down, V toward B, my thumb is to the left. So that means there must be a magnetic field down in this region so that the charge feel the force to the left, right? V toward B, so thumb is to the left, okay? So that's this. I guess I'm just gonna stop here for the first video and see how it went.